we we have around 6 hours left. Today we'll have one session in the morning and one session in the afternoon. And another one session which I could not do last week will be done in the next week, which will be another 2 hour session. So the topics that we will be discussing in the next two three classes are like this. Just 1 minute. So today we will discuss artificial neural network (ANN). In the second half, we will discuss about boosting methods. And in the next week, we will discuss about, I think, no, we discussed not PCA, sorry. We will discuss about K-means clustering. So unsupervised learning, one technique under unsupervised learning, we will. Or in general clustering, both K-means and hierarchical and model-based, all the clustering will be discussed. So today's topic is artificial neural network. So what is an artificial neural network? How does a neuron work in general? So this is how in our body a neuron looks like. Something like this. So this is the head and this is the tail of the neuron, and there are some branches here. And also in the head there are multiple receptors. This is one receptor, this is one receptor, this is one receptor. So we have not learned a system which can learn the world better than our brain or our neural system. So neural network generally tries to mimic whatever neural pattern or whatever way our neural system actually learns from the environment. Neural network tries to mimic that methodology. How? So it says that first we have to learn how our neural network, our body's neural network learns it. So if this is a neuron in general, so what it does that it collects information from here, from this. It has a very easy job. It collects information from each of these receptors. It transforms the information here somehow, and then it passes it on. So to the next receptor, next group. And then there will be another neuron probably back here, which will collect this information. So there will be another neuron which will be back here. Which will collect the above mentioned information through this. And then it will not only collect from this one, but it will collect from other neurons also. So it will not only collect from this particular one, but it will collect from this guy. It will also collect from some other guy, some other neuron, and so on. And then it will again transform it and pass it on. Now, how many neurons we have from our from one corner of our neural system to the brain is not properly known. So there are probably thousands of neurons that might be there. For example, you take a pin and you pinch it on your skin. The skin gets some signal and it passes it on. Now, how many neurons are there from your skin till the brain, or till the, if not brain, till the, I would say, what we call it, the backbone. So, while the extension of a central nervous system is there. So, till the backbone, how many neurons are there, we do not know. So, if we do not know, then if I have to model it, then we have to model it based on certain assumptions, based on certain certain way that and trial and error method that this many neurons will be there and we'll see that how it transforms the data. Also, another important thing is if I ask you, let's say a rasgulla. Okay, there is a let's say a rasgulla is there. Just one. Okay, yeah. So let's say one rasgulla is there, and I try to see that I have blinded the eyes of the person and kept the rasgulla on the hand of a person. Now, what are the various features a person can say about a rasgulla when it is on your hand? The person can say that it is probably circular. The shape can be told. Its weight, it's spongy. These things can be told. Now, I kept it somewhere a little bit away from in a plate, and I do not allow you to touch, but only to see. So when you see, the shape can be also told, the weight can be also told, but spongy cannot be told. Probably the color can be told now, which was not there before. Now, if I want you to taste it, when I allow your tongue to taste it, the shape can be told probably. Weight probably can be told. These two cannot be told because your eyes are closed. You cannot touch it. So you have it in your mouth. Spongy maybe. Let's say I will still give it a thing. Color cannot be told, but taste can be told, which was not there in any of these things. So all I'm trying to say is that we have different kinds of neurons which react to different kind of stimuli. One product, which is rasgulla, might have different characteristics, different stimuli. But not all my neurons will be able to capture all the stimuli. There are certain stimuli that some neurons capture, certain other stimuli some other neurons capture. So keeping in mind, what we can say that if I have multiple features, x1, x2, x3 of a particular product, particular observation, so then multiple features will have different amount of weightage. Sometimes the weightage can be zero. For example, here when I'm talking about the skin, the weightage for taste is zero. Weightage for color is zero. So sometimes there can be weightage. Even for let's say the skin, when I talk about, and I compare it with my tongue and I am discussing about the shape. As skin, your hand will be better, will be understanding the shape better than your tongue. Because tongue gives huge importance to taste and it all of a sudden gives lesser importance to other features that the particular product has. So the weightages are different. So what I mean to say is that if there is x1, x2, x3, these are the inputs like x1, x2, x3, x4, x5, x6, and x7. If these are the inputs that are there, then there are weights also. W1, W2, W3, W4, W5, W6, and W7. So net input to this neuron is basically summation of Wi, Xi. This is the input. Then it transforms it. So some transformation function which makes it information. And that information goes as a round. So that's how the neural network works. Now there can be, this transformation can be of different types. This transformation we do not know exactly what is the transformation function that a neuron uses. So we use different kind of transformation function in our real life situation. For example, some of the very easy transformation function that we use, most common is linear function, that means fx is equal to x, and then comes the logistic function, then comes the probably tan hyperbolic function, step function, linear function within a limit, and so on. So there can be so many different kinds of functions that can be created out of uh, 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 which can be considered as a activation function. So what is a linear function? Linear function, as I just told, just a minute. What is a linear function? Linear function is fx is equal to x. That is a linear function. What is a logistic function? Anybody? Have you heard about this logistic function before?
Yeah, it can be x equals to 1 or 0.
Anybody in the class who have heard about the logistic function?
LNP by 1 minus p, matlab, will it be like fx equals to 1 or 0?
This is 1 by e to the power minus x. Or I can also write e to the power x by 1. This is the equation that we use also in the logistic regression. And then what is the tan h function? Tan h function, it looks like this. Tan fx, tan hs of x is basically sin h2x divided by cos h2x plus 1. And what exactly is just 1 minute. So what is sin h2x function? Basically, sin h2x is equal to e to the power 2x minus e to the power minus 2x divided by 2. So that is basically sin h of x, and sin h of y, cos h of x is basically this function, which is uh, e to the power x plus e to the power minus x divided by 2. So this is I can write it in this way instead of 2x, I can write it in this way. So if I just quickly remove the 2's. So this is my sin hx cos hx, but tan hx is something like this. So if I have to write tan hx in normal word, it will be basically a ratio of these two. So let's just write that. E to the power x minus e to the power minus x by e to the power x plus e to the power minus x. The curve of tan hx looks like somewhere like this. So if I have to draw the curve, it will be defined between -1 and +1. So somewhere like this. This is the zero line. So when your curves are, let's say, for a logistic regression, if you remember, all your probability values are defined between 0 to 1. But if it is by chance defined from -1 to +1, for example, one easy example of this is when we try to estimate the sentiment score. Sentiment score generally is measured in a -1 to +1 scale, positive to negative scale. So when this kind of a scale is there, tan h function looks like this. Up to this, it is like -1. Then it goes to +1. And from here onward, it is +1. So somewhere like this, a sinusoidal function, but defined between -1 to +1, and the value also varies from -1 to +1. So that is one function. Then you can use step function. Step function is defined on the steps basically. It looks like this. It looks like this. And linear finite function is the similar kind of function here. However, it's not a S curve, it's a line curve in between. So anything lower than -1 is, let's say, -1, and anything higher than +1 is 1. And in between this, they follow a curve like this, which is a straight line. So you can use any of this logic function, and basically we have to try out which one looks better. So to model, what we generally do is we first create the overall structure of the model. So in this, in the linear, in the artificial neural network, there are majorly three groups of layers. One is called the input layer. This is called the input layer. This is called the output layer, let's say. And then there are certain hidden layers, which we do not observe how many. So this is, let's say, hidden layer 1, this is hidden layer 2, and so on. So minimum requirement of hidden layer is on 1. Maximum can be huge, can be very high. So what is your input layer? Your input layer basically consists of your input nodes. Let's say I have 7 features per observation. So x1, x2, x3, x4, this will be my input layers. So for our simplicity purpose, because we are going to draw it now, for our simplicity purpose, let's make it only 3 inputs. Let's say x1, x2, and x3. Let's assume that there are 3 inputs. Now there is one hidden layer, which is, let's say, I named them the hidden layer. First one is H11, H12. These are the nodes in the hidden layer. Then H21, H22. Let's say both my layers as 2 nodes. And then there is a Y1. There is only one output. So if I have to by chance think about the neural network that I'm talking about, physical system, then each of these x1, x2, x3 are the inputs, right? And H11 and H12 are the first 2 neurons. The first neuron is H11, which takes this input x1, x2, x3, adds it up with some weightages, transforms it, and sends it to the next layer. Similarly, H12 is a parallel neuron. It's a parallel neuron. It's not a sequential neuron. It's a parallel neuron. It also connects the information from x1, x2, x3, adds it up with certain weightage, and then transforms it with some fx function and passes it on. Now, whatever H11 and H12 is passing it on, that means whatever is their output becomes the input of hidden layer 2. Again, hidden layer 2 gets 2 input, gives some weightage, adds it up, transforms it, and passes it on. So if I draw it right now, if I draw I have drawn the layers. Now if I draw the connections, so let me just choose a color. So let's say this guy is impacting here, This is a first layer. Let's say if I name it W1I. No, W1I does not work. If I just name it, let's say W11, W12, W21, W22, W31, W32, and each of these also gets an error term. Let's say error 11, error 12, which is not given. Then can you tell me what is the input of H11? So we will write it like this: node input and the output. So what is the total input of H11? Can anybody tell me?
W11, W21, and W31.
So Wi1 into Xi, summation of that. So W11 is the weight. Okay. So W11 into X1 is the input. Similarly, W21 into X2 is the plus E11. Similarly, this for this guy, it is W12 Xi, summation of that, plus E12. I write is that's input of 1, 1, and this is input of 1, 2. What is output? Output of 1, 1 is f of input of 1, 1, and output of 1, 2 is f of input of 1, 2. And this f, I can assume as of now it is linear. Let's say I can both the values are same. For as of now, let's assume that. We'll complexify later. Now then what? Then again, this goes here. This goes here. And like this. So let's say I write W dash 1, 1, W dash 1, 2, W dash 2, 1, and W dash 2. So then what will be the node input and output or H21? The H21, the input will be W dash 1I, right? I1. W dash I1 into output of 1I, summation of that, plus error 2, 1. This is basically input of 2, 1. And similarly, input of 2, 2 is equal to 2I plus 2. And this is f of I. Output is what? Output is f of I21, and again output is f of I2. As of now, we assume that these are linear, so this f function is a linear function. Same, f of x is equal to x. Now let's again change it like this. This also impacts here. So let's say this is W double dash 1, this is W double dash 2, and there is another error which is I write EY. So what is the final node? The final Y node. What is the input of that? The input of that final node is WI double dash O2i summation of that plus error y, and the output node is output of y is f of I, right? So these are the maths. Now, if somebody gives me these values of weightage, W1, W2, W3, I can do this cumbersome calculation. It's not so much cumbersome when f is linear, but it becomes very cumbersome if by chance f is non-linear. Let's say if I take f is logistic regression, logistic function, then every time I calculate output, I have to transform it to its logistic form. So the calculation becomes a little bit difficult, but computer can do this calculation. For computer, it is very easy. So as long as I have W1, W2, all these values, W11, W12, W21, W22, and I already have, what do I have in my data set? I have X1, X2, X3. These three values I already have in my data set. Somebody gives me W values, I can calculate on Y. And then I can compare that Y with the actual Y. So whatever is the output of this guy,
So all the functions will be same, or can it be like one function?
can be, each of them can be different.
Okay.
Like for example, for H11 it is, but in general, what we design is, when we design it, we consider each layer having the similar activation function. But that is dependence on the library that we use. Let's say Python library, whatever we use, allows this much. But if you can code, by any chance, if you can create your own activation, your own code for optimization, I will tell you how the optimization works. If you can code on your own, you can keep each of them to be different activation function. No, nobody has to judge. Nobody can say that is wrong. In fact, that is a further stronger, I would say, there's a further stronger what will I call it, than whatever we have. However, you need to have a little bit of good coding background for the same. But it's not very difficult. Means it seems to be initially it seems to be difficult, but over time it's not so difficult thing to do. Now, if I have an output of y, what is my error? My error is basically y actual minus this output of y, whatever I'm getting, square of that and then summation of that. That is my error. So if I have x1, x2, x3 data, and if I have y actual data, I can calculate this OY using all these formulas that I've written at the bottom, and I calculate the error. So what I'm doing here is I am doing a forward feed. I am slowly feeding the data set through my channels towards this side, which we call forward feed, when we are trying to calculate the output of y. However, output of y is dependent on these W1, W2 values. All these weightage values are assumed values. I have to get the best prediction of this value, best estimation of this value. So that procedure will be done through back propagation. What is back propagation? It will start from here and go towards this direction. So that means what? So let me just write down back propagation. That means what? That means that I will optimize the errors based on these two first. Once the error is optimized based on W11 star and W2 star, I will go ahead and do this. Once they are optimized based on this, I will go ahead and do this. So that's how we slowly optimize one after another in artificial neural network. So what do I mean by optimizing? So you see, in normal thing, what we know is that it gets optimized over W11 dash. It gets optimized over W11 dash when, sorry, when this is 0, right? This is what when we do optimize, that's how we do optimization. And in normal world, if I had to do optimization, what I have done, I would have plotted error over W11. And if let's say this is the error, I started from this, I will do slow gradient descent method. Slowly I will change and get the value here. So this is called gradient descent method. Gradient descent has been taught to you in this course?
No, sir.
No, right?
No.
Okay, so what is gradient descent method of optimization? Is that, let's say I do not know the functional formula of this error. It's a cumbersome formula based on what is how the error is a function of W11 dash. This is a very cumbersome formula. So I forget about it. I start with some particular value of W1. All the other values remaining same. All the other W's and X's remaining same. I choose a value of W1 double star. And based on that, I calculate the error values. Let's say the error comes up to be, let's assume that the error value comes up to be here at this point. This is my error value for this W1 double star that I have created. Then what I do? I take W1's value a little bit lower than this, delta W1 double star lower than this, and delta W1 double star upper than this. So let's, for our simplicity purpose, instead of writing W1 double star, let's talk about fx. Okay. Forget about this error. Let's say x and fx, any x and fx. So let's say this is the fx that I'm trying to optimize based on x. So I start with any random x, then x minus delta x and x plus delta x, these three values I find out. So let's say in this curve, x minus delta, I do not know the curve. I cannot see the whole curve right now. But I can see what is the value of x minus delta x, x plus delta x, and x. Now, if these three values are like this, that as I increase from x minus delta x to x plus delta x, if it is going down, if it is slope is going down, then this way it is the minimum. Then I will consider in the next iteration, this will be my x. And slowly I will keep on iterating till I reach this point. Why reach this point? You see, at this point, at the lowest point here, the x minus delta x is higher than this. F of x minus delta x is higher than this point. And f of x plus delta x is also higher than this point. So this is the point where the minima happens. So minima happens when f of x minus delta x is higher than f of x. And also f of x plus delta x is higher than f of x. This is when the minima happens. When it is like this, is greater than fx is greater than f of x plus x, that means it is a downward slope. And when the opposite, let's say this is x minus delta x, this is fx, this is fx plus delta x, this is an upward slope. So by chance, if I have chosen x here, I would have received the upward slope, and then I would have moved towards the negative direction. Instead of increasing the values of x, the next iteration I would have dropped the values of x. This is upward slope. And you see in the maxima, local maxima at least, at this point, what happens? Actually, f of x minus delta x and f of x plus delta x, both are smaller than fx. So nearby values are smaller. So if this is the top value, this value and this value are smaller than this. That's why that's a local maximum. So this is local minima and this is local maximum. So when we optimize, let's say, have you heard about log likelihood in logistic regression?
Yes.
And we maximize the log likelihood, right? In logistic regression by changing the beta values. Or we optimize the error function, whatever you have cost function. So reducing the cost or increasing the log likelihood by changing the beta values, beta parameters in logistic regression that you have learned will follow this method. That they start with some values of beta and they find out at what value of the beta the error is not dropping anymore. Error is the lowest. So at that point they will stop. And these jumps has to be very small jumps. The learning has to take time. The jumps has to be smaller. Why? Because by chance, let's say the curve is like this. If you start giving small jumps, you will reach here. But if this is a starting point and if you start giving big jumps, this is a big jump, then this is a big jump, then this is a big jump, then this is a big jump. These 4 jumps, basically you will see after these 4 jumps, you found that no, my minima is actually here. Because these big jumps will not be able to catch the any undulations in between. So that's a wrong way. Sometimes we miss the local minima when we give big jumps. So the learning processes happens with small jumps. The delta x value that you choose is generally very small, 10 to the power -6. Now that is okay when you have, let's say, x number of 5 input variables, 1 output variable in logistic regression, let's say, 1 output variable and 5 input variables. 5 input variables means you have to estimate 6 parameters, beta 0, beta 1, beta 2, beta 3, beta 4, beta 5. So only 6 parameter you estimate, you are using this gradient descent method, which is this method that I just explained. We are fine. However, here you see only with 3 inputs, I have 6 plus 4, 10 plus 2, 12 parameters. And the number of parameters that I have to estimate, number of weightages that I have to estimate, exponentially increases based on how many layers and how many nodes you have. So I cannot use a very slow learning process when I'm using ANN. I have to use a faster learning process. So what they do is that, okay, you use descent method only, don't worry. However, whenever the slope is high, you give bigger jumps, they say. And whenever the slope is small, you start giving lower jumps. So the jump size, the delta x that you are choosing, should be proportional to the slope, is what they are suggesting. What does that mean? That means I am now optimizing error with respect to W1 double dash, if you remember. So I will say that I will run an iteration of the double dash. I will change the double dash, but this change will be proportional to the slope. And how this function will look like, basically this is a proportional function. This will be alpha into eta. Alpha is the parameter, we call it learning rate. Alpha is the parameter which increases the jump size. and eta is the parameter which reduces the jump size. So this is, we call it stickiness factor. So the higher the value of alpha, the faster will be the learning, the less accurate will be the learning. The higher will be the value of eta, the slower will be the learning and more accurate will be the learning. So basically alpha and eta, these two values make a tug of war with each other. And we choose this alpha and eta at the starting of the model. We choose. So up to what time we will keep on doing this? Up to what time we will keep on doing this? We will keep on doing this till this delta error delta W1 is very close to 0. So is smaller than 10 to the power minus 6, let's say. Till this happens, till the slope is very close to 0, we will keep on doing these changes, using this as my jump size. Now, for W1, this calculation is easy to calculate. So, how if I want to change based on W1, this is easy to calculate. Why? Because it depends on this. Ultimately, it depends on how this is calculated. And this calculation is easy for W1. Why? Let's talk about this. This is W1 double dashed. What is error? Error is, if you remember, that is summation of, or let's forget about summation. Let's only one output is there. Only one observation is there. Will make things. So this is OY square, right? So 2 into YA minus OY. YA is a constant. It does not depend on any parameter. Is actual values. OY depends on parameters. So it looks like this. An output, if by chance if it is logistic, then it becomes further more problematic. But let's assume it is linear. So this is basically, output is basically W1 double dashed output of 2,1, W2 double dashed output of 2,2 plus E of Y, if you remember. So this is easy then. This calculation is easy. Into O21, that's all. That's how I can get the value of this in one go. And I can use this formula when I am calculating. But if by chance, if it is non-linear, if OY was non-linear, then I would have taken a logistic function here instead of a linear equation. And then this differentiation would have been further difficult. Now imagine, instead of W11, if I was doing it for, let's say, okay, sorry, this is not W11, W double star 1. Instead of W double star 1, if I had done it for this one, W1 star 1 1, then what would have happened? Instead of W double star 1, if I have done it for the second layer, then how would have the things changed? This would have been similar. This would have been similar. So this is W dash double 1, W dash double 1, W dash double 1, W dash double 1. Now you see here, W dash double 1 is this value is affecting both O21 output of this and this. No, W dash double 1 is not affecting O22. It is only affecting this node. So only O21 will be affected by W dash double 1. Other things will be constant. So let's write that. So then this would have been YA minus OY into W1 double star into del O21 del W dash double one. Now it basically depends on this now. And what is O21? O21, if you remember, output of 21, I will copy this formula. Output of 21 is exactly like input of 21, and input of 21 is this. So then this formula becomes 2 into YA into OY into W1 double dash. Remember, if there was logistic here, then there would have been double logistic. Here one logistic, here one logistic. I would have created further problem. But because I am assuming linear, this would have been like this. This is W dash 11 into X11 plus, or O11 rather, and W12 double star O12 plus error of 21. And this becomes ultimately easy formula W1 double star into, if I optimize this, this becomes O1. That's all. Now again, this formula is so easily coming because it's a linear function. If by any chance if it had been some other function, it would have been a very cumbersome case, because del x of e to the power x by 1 plus e to the power x is a very bad thing. It is, if I'm not wrong, it is I forgot. So this is a very bad thing. So it was x by 1 plus into x square or something like that nonsense, which is a cumbersome formula. So that would have been another multiplier here. However, your programming, you do not have to do this. Your programming generally does that. So I was asking that what happens that if I can create all my activation functions on my own, separate for each of them. What happens is this calculation you have to do on your own. You have to create these derivation functions also. So which becomes a little bit cumbersome. However, if you are strong in coding and maths, you can do it. It's not impossible. And once you have done it, it becomes faster. So this is how the optimization works. So first I optimize it based on this iteration for W1 double star. That means for this guy. Then I do it for this guy. Then I do it for these 4 people. And then I do it for these 6 people. And I get the optimal values of W1s. Based on that, I do my predictions and I check the prediction accuracy. Now, one thing you have to remember, this, if all the activation functions is considered to be linear, then sometimes you get a one-to-one mapping. You can say that if X increases, what happens to your Y, whether it increases or drops. Because ultimately it's an optimization function, and all your activation functions follows a certain probability. And if it is a linear function, so importance scores of x1, x2, x3, this is a common thing that we try to find out. The importance score of x1, x2, x3 over y is measured by these delta y, delta x1. And if everything is linear, then that is basically this weightage into this weightage into this weightage. So all the paths from x1 to y, the path weightages will be calculated. So x1 to y, there will be 2 paths. One is from x1 to h11, then x1 to h22. Then h11 path will be divided into 2, h22 path will be divided into 2. There will be 4 paths then. And then each of them will be created 1 path. So there will be 4 sets of indirect paths. One is W11 into W11 dash into W1 double dash. Then another is W11 into W12 dash into W2 double dash. plus W12 this path into W21 dashed into W1 double dashed plus W22, no, W12 plus W22 dashed into W2 double dash. So these are the four paths. Two paths gets created from here, from the input layer to hidden layer 1. And then each of them breaks into two other paths from hidden layer 1 to hidden layer 2, and then they joins. So this is the total importance score of x1 towards y. What is the impact of x1 towards y? If somebody say this is your function. However, this is only for linear. If it is non-linear activation functions in between, then this formula will not work. And then the calculation is further cumbersome. So again, your algorithm can give you this importance scores in your computer also. So basically, they can calculate this value in some other way. They can calculate this value and give you the importance scores of x1 towards y. I will stop here before I show you the implementation. If you have any question.
Sir, I have a very basic question, maybe it's a silly one, but then want to understand. So while, I mean, when we are talking about this final error, why we are, I mean, taking a square of it. So, I mean, in a very simple terms, error should be y actual minus the output of y. So why we are squaring it?
Okay, so why we are squaring it is because there can be positive errors and negative errors like YA and OI. YA is an actual term and OI can be your, let's say, predicted term. Let's say there were two values of YA. In the first observation, YA's value was 2. In the second observation, YA's value was also 2. But in the first case, you predicted it to be 1. And in the second case, you predicted it to be 3. So then 1 minus 2 is minus 1 and 3 minus 2 is plus 1. If you just blindly add them, the total error will be 0. We are squaring it up because we want to make sure that the error is positive. Whether it's a negative error or positive error, we convert it to positive.
Yes, but
I
then
could have
can't we
taken
take mod?
Mod. I could have taken mod. This is what I discussed in the first class, that mod will not treat an error of, let's say, 15 and an error of, let's say, 7.5 and 7.5 to be same. So for example, let's say there are two observations. In one observation, you are making an error of 50, another observation, you are making an error of 0. On the other hand, there is another case where both of the observations you are making errors 7.5 and 7.5. A mod term will consider these two cases as similar level of prediction error. A squared term is more conservative. It considers 15 wala error, 15 and 0 wala error to be more error, higher error. Why? Because it is squaring up the error. So 15 square is 225 plus 0 is 225. But 7.5 square and 7.5 square is basically something like 100. If you calculate. So 7 square is 49, so 7.5 square is probably 55, something like that, and 110. So in one side is 225, in another side is 110. I am becoming more conservative when I'm using this square term.
Okay, so basically we are magnifying.
We are magnifying errors. We are amplifying the errors as their size increases.
Sure. Thanks, sir. I think you've explained this before also, but then I forgot.
Yes.
Bye. Thank you.
Anything else? Okay, so if we are okay with the discussions till now, I will share this thing. Let's take a short break of 5 minutes and then we'll come back to the implementation of this Python, of this ANN in Python. So we have to install I will show you whatever we have to install. So be with me. Let's come back in 5 minutes. So let me share the screen once more. And, this is my code basically. So the data set has been taken from one of the GitHub repository, and so I am first of all I'm calling this NumPy for numerical calculations, pandas for reading the data set, and PLT for plot. These are very common libraries that we use. So I'm just calling them, and then I'm reading the data set. So it is reading from this GitHub. It has already read. And if I run the header, you see the row numbers are there first with the customer ID, the surname of the customer, the credit score, geography from where they belong, the gender, the age, the tenure, balance, number of products, has credit card or not, is active member, estimated salary, and exited. So exited is my Y variable. It's a churn modeling in the bank's context, where we are trying to predict that whether the particular person. Oh, I don't think it's in the context of bank. I forgot what context. I think in the bank context only. But whether the customer remains as a as a customer of the bank, and then exited one means he has left the customer churn, and zero means he has not churned. He or she has not churned. And the other basic details of the person, some geographical details, and some some demographic details, and some product purchase transaction related details is given in the data set. So we will try to predict that whether the customer will exit or not, or based on these variables that we have. So obviously then you will see that the shape of the data set, if I just try to create quickly, the shape of the data set is that there are 14 columns and 10,000 rows are there. Now I am breaking this data set between the X and Y. So this is a very common thing that we do. So I'm saying from all the, so see that the first 3 columns, so row number, customer ID, surname, and probably the credit score also. Credit score will work, but row number, which is column number 0 basically, customer ID and surname has nothing to do with if the person exited or not. So 0, 1, 2 is not something I will consider as my X variable. This credit score onward is my X variable that I will consider. So dataset.ilog, this is how we subset a dataset based on its location. And a comma, before comma, I have written just one column, means all the rows I will take. And which columns will I take? 3 to 13. These columns will I take. So 3 to 13 means this is a range. When I write 3 to 13, that basically means, so 3 colon 13. That basically means 3, 4, 5, 6, 7, 8, 9, 10, up to 12. Just 1 minute. It is the range, right? Yeah, so it goes up to 12. So I'm taking 3 to 12 basically. Third column to considering first as the 0th column, third column to 12th column I'm taking. And the 13th column, basically the 14th column, which is first column is 0. So the column with the index number 30 is my Y variable, which is the target column. So if I want to just print them, this is how I get. So it's a array is here, and this is my target column. Now, out of them, you can see that most of them are continuous variable, but geography and gender are categorical variable. So for geography and gender, if they're categorical variable, I can also use categorical variable like in migration. We can use it in ANN also. However, for categorical variables, we have to convert them into continuous, that is numerical variable, by something called encoding. What is encoding? That means if there are two genders, male and female, I will create two columns. One column is male and another column is female. The male column takes a value of 1 when the gender is male, otherwise 0. The female column takes a value of 1 whenever it is female, otherwise 0. Ideally, if there are 5 categories in a categorical variable or n number of categories in a categorical variable, I have to create n minus 1 number of columns, encoded columns. Why? Because this, you see, this male and female that I created, two columns, 1, 0 columns. These are basically complement to each other. So whenever this one variable will be 1, other will be 0. So I do not need both of them. Similarly, let's say geography is France, Spain, and UK. Let's assume. So I create 3 encoders: France, Spain, and UK. Whenever the data set is France, geography is France, the France column becomes 1, otherwise 0. Whenever the data set is Spain, the Spain column becomes 1, otherwise 0. And whenever the data set is UK, the UK column becomes 1, otherwise 0. But do I need the third one? Because whenever the France and Spain, any one of them is 1, UK is automatically 0. And whenever the other two columns both are 0, UK is automatically 1. So I do not need the UK column anymore. I can calculate the UK column directly from the other observations. So we encode one place. So for encoding, we use the pre-processing, one-hot encoder and label encoder, and column transfer. These three objectives we use. In country column, what we do is we use column transfer with the geography as my column and one-hot encoder, comma 1, and then the remainder is passed through. So I create this X. Whatever this CT gets created, so let's just run this much. This one. Let's just add this thing here. Let's just show you what is happening here. If I run this, and if I run CT, so it is a column transfer. It's a column transfer. This thing. Okay, not CT, just one. It's a column transfer object that I have created, and now I'm putting this object in use. Now, if I try to see the X, if I run X, I will get so X1. If I just check the first one, I will get this female tab. Now it is encoded object. This female tab will be encoded. So how do I? Sorry, the not female tab. The geography tab is encoded, which is one ahead of female tab, 608. So if I have some other thing, let's see if I run this. So this is encoded with some number 502 and so on. Similarly, I can also run for male-female encoder. So let's just run this male-female encoder. Once I have run this male-female encoder, let's see what is the X1. So in X1, why did it run like this? Just 1 minute, this should have been encoded. 1 minute. It should have been encoded.
think there is some problem with compose. So it's saying
again?
that yes, it's saying that there is no module name sklearn compose. That's the reason I think it's not converting.
You are getting something like that.
Yes.
Can you share your screen?
Okay.
Gaurav, right?
Yes. Yes, sir.
Give you the share your screen.
Okay.
Okay, so your is sklearn has not installed. So what you write is that in your this thing, can you stop sharing?
Okay.
So just run this thing. So can you add one? So like this, let me share my screen and I will show you. So let's say sklearn is not installed. You open up one blank coding this thing here and then write this sign, which is exclamation sign, pip install sklearn. Basically, sklearn is not installed. You run this first.
Okay.
I have already installed, so I'm not running it. It will take probably 1-2 minutes to run. And then once it is run, you run these two codes once more.
Okay. Another
Okay,
error
let's
I'm
see
getting is
what happens
PIP
then.
install is not recognized.
It's happening now.
No, it's saying that PIP install is not recognized.
Again, share your screen kindly.
Sure.
It should not happen. No, not PIP dot, PIP space.
Oh,
Done. Yeah. Just wait for a minute.
and sir, another question. So what does this remainder pass through would do?
So it's basically taking any one category. So this is this one. Could not fetch. Again, are you using your own computer? Your company's computer?
Yes, company's computer.
Okay, so then you need a you need a basically the pass bypass basically,
Okay.
because it is downloading from this HTTPS and it could not fetch.
Maybe some whitelisting issue.
So we'll stop sharing. Anyway, so this remainder is equal to pass through means that anything which is for the first category 1, it will take as a benchmark. So that category they will. So I told that there are 4 categories. If there will 3 encoders will be created. Similarly, here the first category is taking as the benchmark, and others are basically passing through. That means others are created as a encoded variable. This one, right? So the first one hot encoder, this first entry, whatever is there, it is keeping it, and the remainder. So geography has multiple geographies. So others are being created as a encoded variable or categorical variable or a continuous variable 10. But the first one is keeping remaining same. So this is how I am creating the object.
Okay.
Now I'm putting this object in this whatever X I have already. Similarly, here, if there are only 2 encoders available, means only 2 categories available, we can use level encoder directly. So level encoder means the level itself becomes an encoder. Instead of each each variable, I am creating new variables 1, 0. I create the labels itself as 1 or 0. So that is the label encoder. That's why this female word is still staying here. In the case of your geography, X is changing to some categorical number, some continuous number. But in case of label encoder, it is still remaining there. Now, what I am doing here next is in the scalar model, I am using this training testing split module. What it does, it breaks the X matrix and the Y vector into X train and X test and Y train and Y test. How? With a test size is 0.2. That means 20% data will go to testing data and 80% will remain go to the training data. Random state 0 means it ensures that whatever it ensures replicability basically. When I'm writing 0, whatever result I get in the randomization and whatever result somebody else get in some other computer in the randomization will be remaining same. So this ensures that the data set, the results are replicable. So I'm training testing, I'm breaking it. Next, I'm standardizing. So again, scalar preprocessing, there is a standard scalar object. So this is changing the training data and testing data of the X variables, not the Y variable. Y is a categorical 1, 0 variable, but all the X variables I am standardizing them. Okay, so this female float was not working encoded. Just 1 minute. Let me stop it once and run it from the first one because female was creating a problem and that is showing error now. Just 1 minute. Run once more. This is fine. This is fine. This is fine. Female got encoded or what? No. This is not working. It should remain. Just 1 minute. This label encoder is not working somehow. I have to check why. Oh, did I stop the recording? Okay, sorry.
It was paused.
Sorry. And then another thing was number of layers and number of nodes in each layer can be up to 3. That is another researcher has suggested. But which one is working for your data set, you have to try out. There is no other way to say that. You have to experiment it out and see that which one is working.
I have a question here, sir.
Yes.
So not sure if I have missed this or, I mean, I was struggling to understand. So we have created 3 layers here. So one is the input layer, and then is the second hidden layer, and then is the output layer. So how does the model know that, okay, we have these layers because we have not assigned any variables or, I mean, so we've used classifier.add and then the parameters, but then we've not saved it somewhere to say that, okay, these would be the layers which the model.
No, so I am creating a classifier object. Okay, this is a classifier object. Now classifier.add, this object says that this is a classifier object. This is a structure object basically, which has input dimension 12 dimensions. And then there are 6 nodes in the first node with activation function ReLU. Then another 6 nodes in the second layer with activation function ReLU. And 1 node in the last layer with the activation function sigma. I stopped here means this is my output layer.
Okay, so basically it keep on appending this information. So
I keep
not
on
overwrite
information exactly.
Okay, okay. And I mean, likewise,
There is another library which can create the whole. I will share that thing, but I can give the whole structure in one go. But
okay.
there you cannot. You have to have one activation function for all the nodes together. That was a drawback. Here I can have different activation functions layer wise. If you want to create this thing in one single line, the whole structure, then activation function will be one single for the all of them.
Okay.
Yeah, tell me what is the next question?
I have only this one, sir. Thanks.
I didn't get you. Can you be a little bit louder?
Yeah, sorry. I was saying that I only have this one.
Okay, okay.
Thanks. Yeah.
Okay, so try out with this one and check that whether you so for example you have got a data set on credit scoring. If you remember the credit whether the person will default or not in the logistic regression, you have that data. So I would strongly suggest to try to implement ANN in that data set and try to compare what is the prediction accuracy that you are getting for that data and what is the prediction accuracy that you're getting for this data. I think Saptarshi has taught you this F1 score and recall and precision, etc.
Yes, sir.
Yes. Yeah. So same kind of things. Once you can create this, once you have created this, you can calculate this precision recall in the similar way. So try out the libraries that he has taught in this data set because you have a predicted and testing data right now. So you can use the libraries that he has taught to create the accuracy scores, the other accuracy scores like precision, recall, etc. as well. That's it from me today. We'll take 2 hours break right now. 2 p.m. Professor Sujoy Bhattacharya will come in and he will teach about boosting algorithms. Overall boosting, what is boosting, and he might teach you either AdaBoost or XGBoost, any one of the boosting algorithms which is more common. If time permits, you can ask him to teach the other one as well.
Okay.
Thank you. That's all from me. And I will see you at 2 p.m.
Thank you.